Mrs. Hetzel.
Hi, Mrs. Hetzel.
Okay. And 6th and 7th.
Are you recording this?
Alright. Yes. So that means you need to behave yourself.
Let's say hi without
Yeah.
talking.
Mrs. Hetzel's here. Don't you remember when Mrs. Conley was here and I said, hello, Mrs. Conley? Like that another one? Yes. Just smiling now. Alright, excellent. Okay, so page 17 in your binders. Check. Today's date is the 7th. Yes? Check. Alright, let's talk play Tectonics. Okay, so we talked a little about Alfred Wegener. Yeah, he's German. Yeah. Okay. And Harry Hess and the whole idea of these continents move. And Harry Hess was kind of like, well, how do they move? Alright, we're going to continue on with the how do they move part of things for today. Okay? So the whole idea behind this plate motion, besides the seafloor spreading, well, okay, if the seafloor spreads, how does it spread? Okay, what's causing it to spread? And the hypothesis behind that are convection currents within the mantle cause the plates to move. Okay? This picture came right from your book, so you're reading tonight that you're going to do on pages 42 through 47. You'll see this again. Okay? So just to give you an idea, here's our mantle, right? Gooey molten lava rock, right? Magma, as we sometimes call it. And you see there's some circles drawn in, yes?
Yes.
Okay, so we've got some convection currents. All right, a convection current is the movement of material because of differences in temperature, and that differences in temperature cause things to move around, right? Specifically the density. So Alex, you'd asked before why in the world do I have my lava lamp out for today? Okay, the reason why a lava lamp does what it does is because of convection currents, okay? So what you can't see in my lava lamp is right under here in this section that's covered up with metal, there is a light, and it's a very hot light, okay? So it is shining and using that heat, directing it towards the bottom of this base, okay? And this morning when I first plugged it in, the yellow stuff that's blobbing around was pretty much stuck in one spot because it hadn't warmed up enough. So now it's to the point where it's warming up, right? This blob is warming up because that lamp right there, it's becoming less dense, and things that are less dense than the liquid surrounding them do what? They float, right? So this blob is eventually going to rise up, all right? When it gets to the top, it's further away from the lamp, right? It's further away from the heat source, okay? So because it's further away from the heat source, what's it eventually going to start doing? Cooling off, and as it cools off, it's going to become more dense, so it's going to sink, go back to the bottom, all right? So there's the ooey gooey glob that we just talked about, and you can see it's starting to become more dense, and it's actually going to start moving down, while another blob is doing the opposite, because it's heating up, all right? So this is actually, the process just keeps going up, down, up, down, up, down, up, down, up, down, in a circle, all right? So this is a convection current that we're seeing, all right? Yes, it's a, fancy schmancy fun little thing you can pick up at your local party store, but yes, there actually is a convection current going inside, all right? Question, Brandon? No, it is not. Okay. All right, just to give you another little heads up, so this is a short little video clip. Keep the volume still on.
Something else essential for life on Earth. A way of helping to regulate the planet's temperature. It's a remarkable system. Magma, heated by the core, rises towards the Earth's surface. As it spreads sideways, the Earth's crust is very slowly dragged apart. This moves the continents, creating the Earth's restless and ever-changing surface.
Okay, I think he was from Scotland, yeah?
It was German.
But you get the idea, as that magma is coming up, right, and it pushes out to the side. Remember we talked about seafloor spreading and Harry Hess? Okay? So you're looking at two sides of a convection current. They come up and they push out. And as they come up and push out, the seafloor spreads. Okay? Now keep in mind, on the other side of that, so let's go back a section. Okay? So here's that middle section coming together and pushing out, right? On the other side, what's it doing? Right here and here.
Pushing
It's coming,
together.
whoops,
Around.
it's coming together, right? No, stop it. There we go. Okay? So on this side, it's coming together because it's going out, and then it has to come back in, right? So you've got places where the plates are moving away from each other, and places where the plates are moving towards each other, okay? Make sense?
Yes.
All right. Good to go?
Yes.
All right. Oh, now we don't need to see the Scottish man again. Let's go to that one. All right. I think that's next, yes?
Yeah.
We're back on track?
Yes.
Okay. So, the theory of plate tectonics. Let's get into this a little bit more. So you've got convection currents, okay with that? Big lava lamp, right? All right. So, it's our theory that connects ideas from continental drift. Remember, that's Alfred Wegener. He's German. Yeah. Not to be confused with the Scottish guy. I don't know who that was. At all. Okay. So we've got ideas from continental drift. We've got ideas from seafloor spreading. Remember who is that? H.
Hayward.
Harry. No. Harry Hess. Right? So Alfred Wegener was continental drift. Harry Hess was seafloor spreading. Okay. So the idea of plate tectonics kind of pulls some from Wegener. It kind of pulls some from Harry Hess, and it kind of packages them all nice together in one little compact package. Right. So it explains the formation and the movement of the Earth's crust. Brandon, I can turn it off and put it away if you can't handle being with us today, okay? I know it's exciting, but we're moving on. All right, so it explains the formation and movement of the Earth's crust. So how do we get new crust, right? Seafloor spreading, because new crust is bubbling up at the inside of those plate boundaries. Remember our geochronologists, we looked at the map of the red in the middle, yes? Okay, it's pushing out to the side, so we've got more crust coming. And it also explains how all of our continents are moving. Okay? Check, check. All right. The brain pop talked very quickly about plate boundaries. But before we do that, Jenna?
This is kind of just with like the geochronology that I was thinking about this like for a while.
Yeah.
Know how it's like supposed to be like it's like older rock by the like border of it kind of, and then
Yep.
it's like
On the outside edges?
yeah.
Yeah.
So like the center more would be like the oldest, like in between the sections, right?
The center where you see the red is the new rock.
Yeah.
Okay? And the outside edge, further away from the boundary, is the older rock.
But like further away from one boundary is closer to another, and that's
But you notice you don't see necessarily all of that on this map. Like you remember when you looked at it, there were areas that didn't seem to make sense, right? Because those are the areas that are older that are coming together. Okay. All right. Good thinking, though. Okay, let's talk plate boundaries. There are three major types. Okay. First one is transform boundaries. Transform boundaries are boundaries that slide past each other. So if you're going to do a model of a transform boundary, they go like this. Okay.